Hi everyone, welcome to week 3. This is the first video for day 1. In week 3 we are going to continue with solving trigonometric equations, finding all possible solutions, and then we're going to apply them to a couple of scenarios like polar coordinate systems and complex numbers. So what we have learned is how to use inverse trig function to find angles when the values of the ratios are given. And we also saw that you have to be careful about the quadrants in which these values lie, and that due to the periodic nature of these functions, these values repeat. So there can be multiple results for the inverse function, but the calculator only gives you one answer. So here's an example which hopefully you looked over in the notes. Directly using the calculator for sine inverse of 0.5, 0.5, oh sorry, that's in radian. Let's go back to degrees and repeat. Sine inverse of 0.5 gives me 30 degrees, but that is not the only possible value, because I know that sine is positive in quadrant 1 and in quadrant 2. So I need to find the quadrant 2 angle, and the rule is that whatever acute angle that you find from the calculator, 30 degrees, is going to be the same in the second quadrant, but the actual angle measure is always from the positive x-axis going counterclockwise, which you can find by subtracting 30 from 180. Gives you 150. So we already find that for a given value we can have two answers in this case, which sort of makes sense because we had this discovery that trig values repeat 4 times, 2 times as the positive versions and 2 times as the negative version. And that's because no matter what point you choose on the circle, you can always have a rectangle which gives you 4 points with the same acute angle, theta, and the same trig ratio, differing only in sign. Now we're going to go a step further, and we're going to say, what if we allow for more than one rotation? And in that case, turns out that we're going to have infinitely many solutions. What does it mean for allowing more than one rotation? Is this: if this is theta, I make a full circle and I come back here, that angle, which is 360 degree plus theta, is going to have the same trig ratio. Similarly, I go around one more time, 720 degree plus theta is going to have the same trig ratio, and so on. And you can see this from the graph of y equals sine theta. Y equals sine theta and y equals 0.5, where do they intersect? If I draw the actual graph of sine theta and 1/2, I get these two angles, the 30 degrees and the 150 degrees, 5 pi over 6 and pi over 6, but I also get a bunch of these other angles. So there's infinitely many. Now one way to find this angle is to look what is the difference in going from here to here. So in going from here to here, I'm completing one full cycle, which means I can find this by taking pi over 6 and adding 360 degrees, which is 2 pi, which gives me 13 pi over 6. Similarly, if I take this and I add 2 pi, I'm going to get this point. In the same manner, from this to this is going to be another 2 pi. And from this to the next point is going to be another adding 2 pi. Similarly, going backwards from here to here is going to be subtract 2 pi, subtract 2 pi, subtract 2 pi, and subtract 2 pi. So we can get all the solutions by either adding multiples of 2 pi. or subtracting multiples of 2 pi. And that would give me all the possible solutions, which there are infinitely many of. Now, how do we write that? 2 pi, recall, is also the time period. So the way we write that is that we say the solutions are pi over 6 plus or minus 2k pi and 5 pi over 6 plus or minus 2k pi, where k can be different multiples. So when k is 0, or if I don't write the negative, I let k be negative. For 0, I get pi over 6 and 5 pi over 6. So really what's happening on the circle is, given this point P, theta gives me a certain ratio, but going theta plus 2 pi puts me back at the same place. Similarly, going theta plus 2 pi plus 4 pi gives me the same. And also, going theta and then subtracting 2 pi gives me the same thing. So I always end up at the same point, and so the trig ratio or the value is going to be the same. So let's look at this example. So it says list the general solution and then find 8 particular solution. So the solution, I'm going to start by saying theta is cosine inverse of negative 1 over root 2. Let's see what that comes out to. Cosine inverse of negative 1 divided by square root of 2 gives me 135 degrees. So that's 135 degrees. Let's work in pi. So this is going to be pi over 180. Let's divide by 5. That's 27. Divide by 5. That's 36. Divide by 9. That's 3 and 4. So it gives me 3/4 of pi radian. Now we look at the values. It's ASTC. So cosine is negative here and here, and I have this angle 135. I need to find the second one, which is in quadrant 3. So if this is 135, this angle is 45, which means this is 45. Let's call this theta 1. Then theta 2 is going to be 180 plus 45, or pi plus pi over 4, which is 5 pi over 4 radians. Now my general solution, I can get the same value by keep rotating 2 pi radian extra each time. So solution is going to be, let's call it theta can be 3 pi over 4 plus 2 times k times pi, where k is any integer, or theta can be 4 pi over 4 plus 2k pi, where k is once again any integer. So that is going to be my general solution. Now note that you cannot get 5 pi over 4 from 3 pi over 4, because the difference between them is pi and not multiple of 2 pi. And find the 8 solutions. When k is 0, we already have 3 pi over 4 and 5 pi over 4, which is our first case. When k is negative 1, I have 3 pi over 4 minus 2 pi, which is negative 5 pi over 4, and 5 pi over 4 minus 2 pi, which is negative 3 pi over 4. And this should not surprise you, because remember, cosine is an even function. So cosine of pi over 4 and cosine of negative pi over 4 will be the same. K equals 1. You have 3 pi over 4 plus 2 pi, giving you 11 pi over 4. and 5 pi over 4 plus 2 pi, giving you 13 pi over 4. Similarly, when k is 2, you get 3 pi over 4 plus 4 pi, which is 19 pi over 4, and 5 pi over 4 plus 4 pi, which is 21 pi over 4. So you can find solutions in 0 to 2 pi, general solutions, and particular solutions for different values of k. So I'm going to end this video here, and then we look at some examples in the next video.